Hey guys, BuildZoid here, and today I'm going to be sharing my thoughts on this article by Igor's Lab because a bunch of people have been sort of like getting my attention to it and then going like, "Hey, BuildZoid, we want your thoughts on this." Basically, you should go read this article because I'm not going to read it. It's a bit long. Um, but apparently, a bunch of 3080s and 3090s get very unstable as they approach 2 gigahertz, which, as far as I'm aware, is like an overclock, and like I don't know why you'd expect stability at 2 gigahertz. It's not like if it's not at stock, it's not. It doesn't need to be stable. Um, anyway, but maybe some cards manage to boost up to there under certain workloads. I'm not sure. I don't I don't have these cards in hand, so it's not like I can test. Um, Anyway, but they're crashing. They're very unstable. And Igor thinks the reason why this is happening is because you have cards coming with various different bypass capacitor configurations behind the GPU core. Um, so this is like the inadequate cheap option, then you have like the better option, and then potentially the even better option. And the thing is, as far as I'm concerned, this is like Nvidia screwing up the design guidelines. I wouldn't really throw this on the board partners because, as far as I'm aware, like you can't even ship an Nvidia GPU without running it through Nvidia's Greenlight program. So, like, if Nvidia doesn't approve your PCB design, you can't sell it. And Nvidia designs the capacitor configuration behind the GPU core, like that's set in stone by, or more like the footprint of the capacitors behind the GPU core, that's set by Nvidia. The board partners don't get to play with that. Now, Nvidia does design it so that you have a bunch of options in terms of capacitor selection, so that you can use SMD polymers or 0805 multilayer ceramics. Not pos caps. Okay, like this is one thing I find absolutely infuriating is this entire article refers to the SMD aluminum polymers as pos caps. They're not pos caps. Okay, pos caps are a very, very specific product line of capacitor from Panasonic. Okay, not every SMD capacitor on the planet Earth is a pos cap. Actually, the vast majority of them isn't a pos cap. Okay, or at least I'd assume the vast majority of them isn't a pos cap. I might be wrong about that. Don't make big sweeping statements like that. But like on GPUs, pos caps are incredibly rare. You do not see pos caps on GPUs these days. So pos caps, they look like this. They have markings that look like this. If the capacitor does not look like this, it is not a pos cap. So, for example, there's no pos caps anywhere on this card. There's no pos caps on this card either. There's no pos caps on here. There's no pos caps on there. And nor is there any here or any, like, none of these cards have pos caps. So first of all, don't call the freaking capacitors pos caps just because they're in an SMD package, because this is a very specific series of capacitors from Panasonic. And there's a few different SKU, like, flavors of pos caps from Panasonic. Like, these are also pos caps, but you'll notice they still have the same style of marking. Most GPUs use SP caps, which look like this. They don't have the really white markings on them. And the reason why you'd use SP caps is if you actually look at Panasonic's characterizations, which, give me a second. We're going to pull up TPF, because the TPF series is like the lowest ESR. These suck. Aren't they supposed to be 5? Yeah, it's supposed to be 5 milliohm ESR, TPF. What the hell? That's 6. Why is it 6? Whatever, we'll just select one of these then. Wait, which one did I select? Oh, that's the 220. Oh, that was really dumb. Okay, wait, no, we're not going to use the 220. We're going to use the 330. But the yellow line there is the pos cap, okay? All of the other lines are various flavors of SP caps. This is an impedance graph. Lower is better. Like, the lower this line goes, like at any point in this curve, the lower it is, the better. And the farther out in terms of frequency that line is, like, we want this, like, basically the purple line is like the best. Or the red, the blue, and the purple lines are like the best lines on here, depending on what exactly your goal is. Those are the best lines. The yellow line here is is not really that great. Admittedly, I am comparing it against some of the best SP caps that Panasonic offers. right? Like the LX series here is very low ESR, very low ESL. You have the GX series, which is just the lowest ESR you could possibly go for. And then the CX series is like kind of like a pretty basic, like a pretty normal, high ESR capacitor, relatively speaking. But you can see that basically the pulse cap kind of sucks. Then if you look at the ESR graph, it still kind of sucks. None of the cards use pause caps. Don't call these pause caps. They're not pause caps, okay? Um, so very much, where's the product catalog? Yeah, so that's what a pause cap looks like. That's what an SP cap looks like. And fun fact, Panasonic isn't the only manufacturer of SMD capacitors on planet Earth. You've also got Kemet, who have cocaps, which SP caps are conductive polymer aluminum electrolytic capacitors. Then you've got your conductive polymer tantalum solid capacitors. Which technically, like, the polymer is still solid, so yeah. Like, there's no liquid in these if you break them open. And actually, in my experience, if you cook like, the tantalum capacitors are actually more sensitive to overloading than the aluminum capacitors are, and they smell really bad when you overheat them, like really really bad. Worst smelling capacitor ever is tantalum capacitors, as far as I'm concerned. But anyway, so Kemet have cocaps, which are also a type of conductive polymer tantalum capacitor. APAC makes conductive polymer aluminum capacitors in an SMD package. And the thing is, so, like, just because it's an SMD capacitor, don't call it a pause cap, because that is a Panasonic product line. It is not a general term for SMD polymer capacitors. I would refer to them as SMD polymer capacitors because that's the most reliable way of not getting them mixed up with, like, SMD multilayer ceramics. Actually, the funny thing is you can technically get, like, the CAN type capacitors with adapters for SMD mounting, which is just, like, that makes it extra confusing. But anyway, so yeah, not pause caps. None of those cards have pause caps. Actually, here's a card that does have pause caps and SP caps at the same time. How special is it? So this, right? So these are pause caps, the ones with the really white markings, and then all of this right here, those are SP caps. So that should give you some idea. And it's kind of funny how you get this mishmash. And also, this is consistent on GTX 590s. Like, every single GTX 590 I have doesn't only have pulse caps behind the second GPU core. I'm not entirely sure why. But it's just kind of an interesting thing that it seems to be standardized to have one different capacitor on one of the cores, whereas on, like, the primary core, you only have the pulse caps. But anyway, we're not here to talk about GTX 590s. We're here to talk about RTX 30 series cards and the fact that they don't use pause caps. But anyway, so the pause caps thing aside, yeah, like, even as great as SP caps can be compared to, like, regular through-hole capacitors, like this is a regular through-hole capacitor, and admittedly, I didn't pull up a, like, you don't see Panasonic through-hole capacitors used on, like, GPUs and motherboards, because Panasonic doesn't really make a lot of, like, Panasonic doesn't make a lot of really good ones. If you want a lot of different, like, high-performance aluminum like, through-hole capacitors, you'd be going for, like, Nippon Chemicon, Nichicon, or if you're going cheap, you go APAC. You don't really see Panasonic capacitors. But anyway, like, the thing is, in terms of the impedance graphs and the ESR graphs, there shouldn't be too much difference between the different manufacturers. Like, basically, maybe some of the other, like, better manufacturers would have lower, like, have this same curve, but it would be shifted down a bit or something like that. But ultimately, like, what's worth noting here is you'll see that the bottom of this curve is at, like, 0.04, like 0.004, and it bottoms out in between, like, 0.1 megahertz and, like, 0.2 megahertz, right? So that's like 120, 150 kilohertz right there, where it bottoms out. If you compare that to the SP caps all basically bottom out at 200 kilohertz to, like, 3 to 400 kilohertz, right? 300 to 350 kilohertz in terms of where they bottom out in terms of impedance. And then you'll also notice that their ESR graphs are just lower, right? Like, so that red line is bottoming out at 0.02, whereas this is bottoming out at, like, 0.04 4-ish again, right? So anyway, and the reason why the ESR and the impedance here are very important is because this basically tells out, so basically capacitance is how much energy can our capacitor store, and the impedance and the ESR is how quickly can we get energy in and energy out. And with GPU cores, the whole purpose of the capacitors sitting behind the GPU, directly behind the GPU core, is that when the GPU core goes from doing a little bit of work to doing a lot of work, the current draw drastically changes. So suddenly, out of nowhere, you need a lot of energy. And how do we deal with that? Because you're never going to build a voltage regulator that's fast enough. The voltage regulator is never going to be close enough that, like, you have power plane impedance in the way. So you can just about basically give up. You're never going to get rid of the bypass capacitors behind a GPU core. You need them because you can't actually design a voltage regulator that is going to keep up with the, well, unless you had like a fully integrated voltage regulator. But within the realms of things that like companies that aren't Intel can do, you need you need your bypass capacitors behind the core. And even with a fully integrated voltage regulator, you do still need bypass capacitors so that you can bypass the fully integrated voltage regulator. Which then needs significantly less output capacitance, but you don't get rid of the bypass capacitors. Like it's less difficult to bypass like Haswell CPUs and that kind of thing. If you look at the back of a Haswell CPU, you'll notice there's very few capacitors on them compared to like other CPUs that don't have fully integrated voltage regulators, but still, you do still need some form of bypass for even those, just because you're never going to get like the voltage regulator to follow the demands of the GPU core or the CPU core perfectly. So whereas capacitors, being passive components, they don't care. As soon as the voltage drop, as soon as the voltage behind the GPU core starts to drop because the GPU core is starting to pull more and more current out of nowhere, the energy stored in the capacitors is going to start getting out of them through the impedance. Right, through the impedance of the capacitors. And that's kind of the reason why you see the mix of different capacitors behind the GPU core, right? You have your SP caps, and then you have all of the little SMD multilayer ceramics. And the multilayer ceramics have much, much lower impedance, like have low impedance at much higher frequencies. So this is like a 47 microfarad multilayer ceramic, minimum impedance at 1 megahertz. And it's like 2.5 2.5 milliohms of impedance. So very low impedance, very low ESR, all the way into just ridiculous frequency ranges compared to, well, basically anything right here, right? Like you can see this graph, just lower, like higher frequency, very low impedance. Then we've got like a 10 microfarad 0805. Again, you know, that shifts the frequency. Again, you get even lower, like you don't really get lower impedance, but you do get low impedance at a slightly higher frequency. And then if you start going like, and these are 0805s, and so 0805s, just because of how big they are, they can't really get super low impedances, but you'll notice how behind the GPU core, you have your, well, this card's actually terrible for that. This card's best. This has the most diverse mix of capacitors. So, I clicked on the wrong image. Come on, open. There we go. So you have your 0805 multilayer ceramics, then you have like 0603 multilayer ceramics, you have 04, I think some of those might be, no, I don't think I'm seeing any 0402s, but you do see a lot of 0201s. And so with the smaller capacitor packages, basically this curve that you have here just keeps getting shifted further and further into the into higher and higher frequencies. And that allows you to switch out higher and higher frequency load transitions. Right. The problem, of course, with the really small, very high frequency capacitors is that, well, they don't have a lot of capacitance because they're very small. So you can't store. So while they're excellent at like storing energy and releasing energy super quickly, you can't actually store a lot of energy in them. So that's kind of the downside there. But when it comes to the bigger 0805 multilayer ceramics and well, SP caps and pulse caps, they're actually kind of equivalent. Like, you know. Like, technically, you could get, like, a 560 microfarad SP cap into the position. Blech. Yeah, like, you could technically replace these 470s with a 560 SP cap. But the thing is, those get very expensive, and you really don't see them very often. But the 470 microfarad SP caps, like, if you buy 10 and like you'll notice like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 10 multi-layer ceramics. Yeah, you could get like 10 of these 47 microfarad multi-layer ceramics and just have 470 microfarads of capacitance, but with this performance curve instead of this performance curve, right? Like these performance curves right here, right? So you could have the same capacitance at a lower impedance, and that's better for filtering out the switching noise that GPU cores produce as part of being GPU cores. And the other thing is, also when you put a bunch of capacitors in parallel, this effectively gets shifted down. Because if you have 10 caps in parallel, their ESR, the equivalent series resistance, is also in parallel. So effectively, you get 470 microfarads at like 1/10 the usual ESR. And so you actually get something that's even better than what you get. Like individually, like basically the curves of these capacitors sort of stack in a beneficial way. And so you get even more performance out of it by putting a bunch of them together. And so, yeah, like multilayer ceramics are just superior to your, SP caps and other like SMD aluminum polymers. Like they're just better than those. And that could definitely affect the stability of the GPU core. Like if your voltage drops during a load transition, then you're going to have instability. That's going to show up as artifacting or crashing or, the usual instability indicators. And so the thing is, though, like the thing. The thing is, though, like all of these capacitors, like 0805s and the SMD, polymers, like these are relatively low frequency capacitors. They're really not like you can see it in the performance curves, right? Like this is like 100 kilohertz where they bottom out, like hundreds of kilohertz where these bottom out, megahertz range for these, right? This is like 2 megahertz, so it's really not that crazy fast. So the thing I'm wondering is like just stab one of like what I want to see is just stab a 3080, like take a bunch of different 3080s with different capacitor configurations and stab them with an oscilloscope. You shouldn't even need that good an oscilloscope. You should be able to measure this quite easily, because like if there is a difference, it should be pretty easy to measure. Because these aren't like super high frequency capacitors. So that's the thing. So this theory looks correct to me. The problem I have with this is I wouldn't necessarily blame it on the actual GPU manufacturers because as far as I'm aware, if you're making an Nvidia GPU, you need to get it approved by Nvidia. Like your PCB design, you need to get it approved by Nvidia. The capacitor configuration behind the GPU core is, like a design guideline you get from Nvidia. Like the footprints for the capacitors, you can't change that, right? Which is why if you look at some of these cards, like actually, Zotac seemingly did change that. Yeah, you don't see all of the padding for the multilayer ceramics, but if you look at like MSI's, yeah, MSI didn't change that. So if you look at MSI's card, right, you'll notice that you still have the pads for all of the little multilayer ceramics over there. Right, that's what those copper tabs are sitting around the capacitor. Like those are for the multilayer ceramics, and it's just like so. So the capacitor configuration is kind of set in stone by Nvidia. And if Nvidia says, "Hey, you can replace our crazy multilayer ceramic configuration with SP caps," like I'd blame Nvidia for this because it's just like Nvidia should know better than to tell their board partners to like. You can replace the expensive capacitors with cheaper capacitors because it's like everybody's going to replace the expensive capacitors with the cheaper capacitors. Of course, they're going to do that. Right. So it's just kind of like don't send out design guidelines that allow you to do stupid things like this. Speaking of stupid things, like what I've noticed is like so Zotac uses like 330 microfarad SP caps. We have Gigabyte using 470s. Which the 470s do perform better than the 330s, just by the way, they do. You also have Palette, where, like, Palette is an interesting mishmash. So they spent the extra money on the multilayer ceramics, but then they cheaped out on the actual SP caps, because these are 220 microfarads. So those are some of the lowest capacitance SP caps that you can get behind a GPU core, like behind a 3080. So that could be interesting because, like, yeah, you have very low impedance, but now there's like 200 microfarads less capacitances. Could that cause issues compared to some of the other cards? Maybe. Um, then this, I suspect these are 47 microfarad multilayer ceramics, and I suspect that because they're bright, like they're very yellow, and in my experience, a lot of the time the really yellow 0805s are 47 microfarads. Just like I had a 290X where like there was a bunch of really yellow 0805s, I pulled them off and they were 47 microfarads. Then I actually regularly buy 47 microfarad 0805 capacitors just for, you know, my capacitor modding adventures. Because they're great, they're amazing. You get 47 microfarads, very low impedance. Like you can smack them basically at, like they're small. You can smash them basically anywhere. You can whack them on memory chips, behind GPU cores, on the outputs of VRMs. You can put them anywhere. They're awesome. Yeah, but the 47s, they're all really yellow. Like compared to a lot of the other capacitors out there, they're very yellow. And so I suspect these might be 47s, which would be really cool because they're actually really expensive. They're like disproportionately expensive compared to your 10 microfarad 0805s because like getting that higher capacitance density in the same size package actually gets you like it's you know they charge a premium for that because it's like it's the same size but it 4 times the or almost 5 times the capacitance of some of the other variants. So yeah. Um, so this could like these are pretty cool. MSI, I think these are just 10 microfarad, just judging by the color. They could also be 220s or something. Like that's the thing. It's really hard to judge, but yeah. So like, I feel like, you know, Nvidia should have probably set out a design guideline that was just like, look, you need at least one set of multi-layer ceramics if you're gonna be building these cards. Um, because it doesn't make sense to me that, you know, it's just like, yeah, you can ship these with a cut down bypass filter, with a cut down bypass capacitor configuration and call it a day. Which would like, yeah, like that causing instability, that would not surprise me. But it really shouldn't be causing instability at stock. So I'm guessing that's the whole 2 gigahertz. Like, yeah, if you're overclocking and these are unstable, then like, this is why I complain about, like, this is why I pay attention to capacitor configurations in on GPUs, right? It's just like, um, yeah, like, this is why one of the reasons why I cap mod GPUs is just like, if you get better voltage regulation, you get better overclocking because your maximum sustainable frequency is directly tied to the minimum load voltage that your chip is receiving going through its load cycle as it load cycles. Right, so yeah. Also, I'd like to point out that apart from the fact that there is still enough high frequency garbage from the voltage converters, VRMs really don't produce a lot of switching noise. Like if you like they really really don't. Um like if you have a VRM running and there's no actual load on it, you can get like 20 millivolts peak to peak. And then you'd start like a GPU workload or 20 millivolts peak to peak with my measuring equipment. Um, if I measure, and then if you compare it to what you see when a GPU is actually running, um, like like a lot of GPUs run with like 200 millivolts peak to peak behind the core. On my Rigol DS1054Z oscilloscope, which isn't the world's most sensitive or fastest oscilloscope, and I'm using the 10x probes to measure a, you know, low voltage signal. So like I'm not even getting the highest detail measurement I could, and I'm already seeing 200 millivolts peak to peak, which is just ridiculous. But the VRM on its own, it'll produce like 20. So the VRM really doesn't produce a lot of switching noise, like compared to what the GPU core does. Like the GPU core is like it, yeah, like it's the amount of noise it produces is insane, and it's been going up as GPUs have been getting more and more advanced, which is you can kind of see that with the GTX 590, right? Like this is a high current draw GPU. Actually, I think I should have pulled up a 580 for this. That would have been a better example. Let's take the Nvidia reference design, right? So if you look at a regular 580, like you'll notice that the capacitor configuration here, like first of all, you've got these large multi-layer ceramics, which incidentally, the 1206 packaged multi-layer ceramics are worthless. Like they literally have the same performance curves as your SP caps, which is just like why bother using those? Um, but then you have like a couple 0805s. Like this really doesn't have the like complexity of bypass capacitors that you see on the 30 series, because these cards have, run at higher frequencies. They create worse load transients, and so this was acceptable for GTX 580. It would not be acceptable for a modern GPU. Because these GPUs just didn't have as much load cycling as the modern ones do. But anyway, so yeah, like this seems totally reasonable to me. I also find it that kind of like, hey, Nvidia, maybe you should, I don't know, tell your board partners how to configure the bypass for the core. Like, come on, why like, what's the point of sending out a reference PCB design if you don't tell everybody how to, like, if you don't tell people how to implement it properly? Um, so yeah, but I'd blame Nvidia for this. Just straight up, I would blame Nvidia because it's their card. They design the they set the design guidelines. And if the design guidelines said, "Hey Zotac, you can do this," and Zotac does this, and then it doesn't work, it's like Nvidia should have probably like not said that this is okay, because like come on. At the same time, like the thing is, if the cards aren't crashing at stock, though, I really don't see the issue. And especially like the Zotac Trinity cards, like if we look at Tech Power Up's review, like so Igor says in his article that the cards get unstable at like 2 GHz, but uh, this doesn't run at 2 GHz. This runs at like 1755 most of the time. Right, like this is a really like it's nowhere near to 2 GHz until I guess the end of the workload right there where it spikes up to 1980. So I guess you might be running into some issues where certain workloads are so light that the GPU core goes to like crazy high frequencies. But lighter workloads, actually no, that could be interesting. So the funny thing about workloads is you can get workloads that average less power draw and run cooler, but because of how they might be running cooler because they're like stalled out on memory access, or they're just really weird in terms of how they run. So you could have a workload that actually has a relatively high average frequency, doesn't really pull that much power, and also causes just disgusting transient loading on the VRM. And so then you'd have something where it's like that could be really unstable. Or there might be just like a section in a game where suddenly the GPU decides to boost like crazy high, which like this is just a side effect of boost algorithms being annoying to test for stability, where it's just like, yeah, you test your stability in one workload that runs at 1700 megahertz, and then you run another workload that runs at 2 GHz, and you're screwed, right? But anyway, so the Trinity cards, like I'm not sure if I'm getting like, because the thing is, I don't think there's many cards running 2 GHz stock, right? Let's just go through all these. So 3090 Strix, clock speeds. Okay, this blips just above 2 GHz sometimes. Most of it's approaching. Yeah, it's actually kind of running right around 2 GHz, isn't it? So there's the Strix. Let's see what MSI's got. Also, okay, this one definitely, you get a period of 2 GHz for some time, and then it drops down into the high 1900s. Then we have this also approaching 2 GHz. So yeah, I guess board partners like the thing is, yeah, if they're shipping the cards with overclocks where the cards are unstable, and it's a side effect of their crappy capacitor configuration. It's just like this is the thing. It's just like don't send out overclocked GPUs if you're not stress testing them properly. But at the same time, like these are going to be super annoying to stress test, and also you do have like chip to chip variance in terms of like the behavior of the actual silicon. So like some cards will potentially produce worse transient loading just because the GPU core on them is leakier or something than other GPUs. And you will also get like some variance in terms of max clock. Like some cards will boost to a higher clock speed at stock settings than other cards, just because again leakage is a thing. So yeah, this palette card, which in my opinion has a very weak capacitor configuration. At least it mostly runs at 1800 megahertz, so that shouldn't really have an issue. Then we have Gigabyte with 470 microfarad SP caps, and this runs where? This runs around 1800, so I'd assume that shouldn't have too much of a problem. Um, yeah, so that's like if you're overclocking and the cards get unstable because of the crappy capacitor configuration, it's just like, well, that's what you pay extra for with the cards designed for actual overclocking. Though I really didn't think this would be such a like the thing is when I did my video of the 3080 Trinity PCB, I didn't really pay that much attention to the GPU core capacitor like bypass capacitor configuration because I really didn't think it would have that much of a like it would be that important. Because generally speaking, in the past, like you've had Nvidia GPUs where they'd just be missing capacitors completely, like they're just not there. And even here, right, like there's a bunch of blank spots, right? Like there's a blank there, there's blanks there. Like a lot of the really small capacitors, they're gone. Also, these are bright yellow again, so these are probably 47s, which wouldn't surprise me. Like Nvidia likes to splurge on their PCBs in like the weirdest places. You know, it's just like, yeah, let's spend. Well, actually, no, to be fair, the capacitor configuration, I'm a big fan of this. Like SMD, you know, capacitors are awesome. So yeah, I'm a big fan of what Nvidia has done with their Founders Edition PCB in terms of the capacitor configuration. I'm not a big fan of the fact that they've shoved everything onto the smallest possible PCB so that it like the heat density is higher than ever. Right? It's just like, yeah, so we kind of suck at designing heat sinks. Let's make it even harder to cool our card. Um, anyway, but the thing is, like, you can get 1080 Ti's with just like like completely missing capacitors in their default configuration, right? Like, pretty sure, yeah, this is one of those where you look at the back, ta-da! Like, admittedly, they filled out a bunch of like small multilayer ceramics in those places, but ta-da! Like, those are just gone. So I guess with this card, it was identified that, you know, the high frequency filtering was more important than having a bunch of capacitance. But what else do we have? Let's see this. Oh, actually, let's go look at the Zotac card. Though this is the amp, so I would hope that they didn't do anything to... Come on. Yeah, no, so what do we have there? I can't even identify the branding on these, but yeah, like the thing is, there's other, like with the capacitor configurations, there's also the, like one of the sort of weird cost considerations is actually you spend less time on the pick and place machine if you use bigger capacitors instead of more smaller capacitors. That's another like, you know, and it might like the thing is like if you're placing, you know, if you replace one of these large capacitors with 10 smaller capacitors, that's basically 10 times more time on the pick and place machine than if you were using the bigger capacitors. So that's another consideration is not only are the multilayer ceramics more expensive per microfarad, so if they're like if the design, because I assume the design guideline is something like you have to have this much bypass capacitance behind the core. Because that's a lot of the time what you'd see for like like Intel has that kind of guidance for a lot of their like motherboard designs where it's just like your CPU socket cavity should use this many capacitors and you should be aiming like with this much total capacitance. Well, actually, Intel straight up tells you to just use like a very specific value of multilayer ceramics a lot of the time. Like some of the boards are like use 50, like use 20 10 microfarad capacitors for bypass or something in the CPU socket cavity. So yeah, I'm surprised like Nvidia one has such loose design specifications that this can be an issue. At the same time, they've had the like loose design specifications for a pretty long time. Yeah, and then we have EVGA where EVGA is just like no bulk. Right? Like this is significantly less capacitance, and yeah, it's going to have the lower impedance by comparison compared to the larger capacitors. But yeah, I'm not sure how this works out. And then of course you have all of these missing capacitors, but that's just normal. You see that everywhere. So yeah, it's just like So like if it gets unstable when overclocking, I don't really see a problem. If it's getting unstable at stock because partners are shipping cards with too high like overclocks out of the box, then it's just like partners need to like properly stress test their freaking cards, right? Like that I would actually blame for the like I'd blame the actual board partners for that in that case. And if it's a case of like Nvidia didn't give us clear enough design guidelines, then it's just like then it's Nvidia's fault. Um, but yeah, like I'm surprised that this has actually become an issue because historically, right, like a lot of the time, like there's a lot of GPUs where if you remove a bunch of the capacitors behind the core, they're still going to run stock fine. Um, so yeah, I'm really surprised that um, this is an issue. Like it makes sense that this could be an issue because again, like multilayer ceramics have far better impedance at high frequencies than your SP caps do, but like I'm surprised that like this wasn't caught in some kind of QA. Also, I'd really like to see oscilloscope measurements of these cards, like because it should be trivial to measure this. Like we're not talking like super high frequency stuff. Like stab the like Igor has a bunch of cards. I'm pretty sure Igor has an oscilloscope. Please stab some of them. Like I'd like to see oscilloscope graphs because and actually I'm assuming that actually do I still have that? No, I have the front for some reason. Oh no, now these are all on the. Oh, there we go. So I'm assuming that these two pads right here are for VCore. Like one of them's ground and one is VCore. I would solder I would stab those two pads right there. Because the thing is, if you measure directly off of a capacitor, you don't like the fact that you're measuring across a capacitor that's populated will skew the measurement. And so if you're like measuring across, like don't measure off of the capacitors that are getting replaced, is what I'm trying to get at, right? Like don't measure across the caps that are getting, like don't measure across the thing that is don't measure across the variable. That's kind of like that's probably going to skew the measurement. So yeah, I would just basically choose a random V-core capacitor, maybe around the center of the core, and measure off of that, probably right here. Like, because those are some of the biggest pads there are. Maybe this cap over here. I'm not sure if that one's V-core. It might be. Maybe this one over here, right? Like, there's a bunch of options. Just measure off of one of the caps, and measure it all. Like, the thing is, it's unpopulated on like all of the cards, right? Like, you can see it right here. Um, so yeah, I'd measure. You know, like I'd love to see oscilloscope shots because if there is an issue, it should show up on an oscilloscope. Though I wonder if it might not be like a 10 millivolt difference because that's the other thing is like even like if you're really right on the edge of stability, very small differences in voltage regulation can make pretty drastic differences in terms of artifacting and crashing and that kind of thing. There's also temperature effects to consider, and the thing is also like your power supply going into the GPU can actually affect what comes out of the VRM. Um, so if your power supply is not capable of keeping up with the demands of the 3080, then that could also translate into some instability that's then exaggerated by a weaker bypass capacitor configuration behind the core, right? Because like that's kind of the thing is like if you start with noisy power at the start and then you don't really do a great job like so you have a relatively noisy power supply, then you don't really do a great job of cleaning that up when you get to the GPU PCB. So some of that's going to pass through the VRM. On the output of the VRM, you now have not that great bypass, like not that great capacitor configuration. So that's still not going to clean it, like still not going to clean it up. And then you get like, oh, and now it's really unstable. Like now you have it being more unstable because of the combination of both power supply and the weaker capacitor configuration. But like, there's a lot of variables to this. I really think like I'd love to see oscilloscope shots. And yeah, like it doesn't seem unreasonable that this could be an issue. Um, I'm just surprised that Nvidia put out a guideline where it's like, no, you don't need to only use like you don't need to have one of these multi-layer ceramic groups. Um, so yeah. Anyway, that's it for the video. And my God, this one's really long. But like, I don't have enough information. And apparently Zotac has tried to test this out. Also, Asus, like I've heard, apparently there's an Asus 3090 Strix or 3080 Strix with like SP caps behind the core. And I can't find a picture of it. Oh wait, what's this? No, that's a 1660 Ti. Not the same card at all. Yeah, like I'll just end it here because I don't have enough information. It does, like what Igor is saying here makes sense to me. Like, yeah, if the cards are, you know, overclocked to higher than stock frequencies and then they use a weaker capacitor configuration, then yeah, they're going to be unstable. I'm just surprised that like QA didn't catch this, that Nvidia didn't put out a more strict design guideline, or that like I'm surprised this is an issue. Like, I'm really surprised that this is an issue. It's just like the other thing is, like, you don't even necessarily need to stability test it. You could just stab the cards with an oscilloscope and go like, wait a minute, these have 20 millivolts more ripple. Is that potentially going to be a problem for stability? Actually, what would have been better is if Nvidia just had like a guideline, like you need this much, like this level of voltage regulation behind the core. We don't care how you achieve it. Like you can't have more than 200 millivolts peak to peak behind the core. There, figure out how to like solve that yourselves. Not our problem. So yeah. Anyway, I guess that's it for the video. Like, I'm kind of annoyed that like I feel like this is kind of a non-video because there's not much information here, you know. And it's not like I have the cards in hand, and I mean I unfortunately don't really like, as much as I have great resources when it comes to motherboards. I don't really have a lot of access to like I can't really talk to anyone too much about like GPU PCB design, unfortunately. Or like what kind of decisions are made in that, and how the cards are tested. But anyway, yeah, that's my thoughts on this. So I guess thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. Otherwise, there's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. Both of those, both the Patreon and the Teespring store, help out immensely with running the channel, so it would be really appreciated if you check them out. That's it for the video. Thank you for watching, and goodbye.